The SPDF orbitals are a highly accurate representation of how electrons exist and behave in atoms. We will also be covering the four principal quantum numbers as they are essential for understanding SPDF orbitals. In a previous video, we covered how the Schrodinger's model works and what atomic orbitals mean. You should check out that video for some prerequisite knowledge for this one. So as a recap, electrons don't just orbit like planets. They exist in 3D regions called orbitals. Each shell has its own set of these orbitals, and the shapes get more interesting as we go higher. This is a bit of fun fact on the nomenclature of SPDF orbitals and why they are named as such. When scientists first studied the emission and absorption spectra of atoms, they noticed certain series of lines. They categorized these lines by their appearance: S for sharp, P for principal, D for diffuse, and F for fundamental. S orbitals are spherical, one per shell, simple and symmetrical. Think of it as the electron's cozy little bubble around the nucleus. I'll explain more on what nodes are later. So this is a diagram showing the different orientations of a p orbital in space, as we have to remember that this orbital takes into account that atoms appear in actual realistic 3D space, not just 2D space. P orbitals appear from the second shell onwards. There are three per shell, arranged along the x, y, and z axes. These are like three tiny dumbbells surrounding the nucleus. D orbitals start in the third shell, and there are five of them. They look like four-leaf clovers, except for the one in the middle, which looks like a donut in the middle of a dumbbell. This configuration is the most interesting. Take note of it. These orbitals let atoms form complex bonds, such as p-pi d-pi interactions. F orbitals, starting from the fourth shell, are very special. 7 orbitals per shell, 2 electrons in each orbital, with shapes almost like an explosion from fireworks. Electrons here are high energy, filling some of the most intricate spaces around the nucleus. Electrons fill orbitals in a specific order: S, P, then D, and F. Lower energy orbitals come first, or S and P orbitals first, then higher D and F orbitals. This pattern explains why elements have the chemical properties they do. So S, P, D, and F orbitals aren't just numbers. They are 3D homes for electrons. Now let's see how they are related to quantum numbers. The principal quantum number, n, is basically the electron's address. It tells you which energy level the electron lives in. The higher the value of n, the farther the electron's average distance from the nucleus, and the higher its potential energy. Imagine n as floors of a skyscraper. Higher floors are further from the lobby, and it takes more energy to get there. When n increases, three things happen. The orbitals get bigger, the electron's energy increases, the electron has more nodes, which are regions where the probability of finding it is zero. Think of nodes as no-go zones, like floors in a building that are sealed off. Nodes exist because electrons exist as a wave function, so there must be points where they have zero amplitude and equate to zero, meaning there is zero probability of an electron being there. Each value of the azimuthal quantum number corresponds to a specific shape. L equals 0 gives us spherical s orbitals, L equals 1 gives us dumbbell-shaped p orbitals, L equals 2 creates clover-shaped d orbitals, L equals 3 unlocks the wild multi-lobed f orbitals. Why does a higher L value give weirder shapes? It's because L corresponds to angular momentum. More angular momentum pushes the electron density outwards and sideways, distorting the simple sphere into more complex patterns. The periodic table's blocks are simply just the angular momentum quantum numbers printed in color. S block, P block, D block, and F block are the angular momentum quantum numbers being filled. Everything from the softness of alkali metals to the colors of transition metals arise from the L of the highest energy electrons. There are some very interesting properties of the azimuthal quantum number. As described by its other name, angular momentum quantum number, the azimuthal quantum number governs the orbital angular momentum as described by this formula over here. An angular node is a region where the electron probability is exactly zero because of destructive wave interference. Magnetic quantum numbers tell us the orientation of the orbital in 3D space. These orbitals are not arbitrary and come from the mathematics of angular momentum in quantum mechanics. Why is it called the magnetic quantum number? Because the orientation of the orbital changes if there's a magnetic field nearby. The presence of the field breaks symmetries of space, so orbitals that used to be equivalent suddenly behave differently as some align with the field while some resist it. This is why spectral lines of atoms split into multiple components when placed in a magnetic field. This effect has a fancy name, the Zeeman effect, as the number of split lines is controlled by magnetic quantum number. Now, calling it spin is a bit of a misleading fact. Electrons don't literally spin like basketballs. If they did, they'd have to rotate faster than the speed of light just to match the magnetic moment we measure. So instead, physicists call it an intrinsic form of angular momentum, a built-in quantum twist that every electron carries. Imagine each electron is born with a tiny magnetic field, like a microscopic bar magnet. Depending on whether its spin is plus half or minus half, the magnet points in one direction or the opposite direction. Place an electron in a magnetic field and it behaves differently depending on its spin. This isn't just theory and you can actually measure this. Hope you enjoyed learning about SPDF orbitals and the quantum numbers in this video. Thank you for watching.